This is a differentiation review. Let's start off with some fundamentals. Suppose y equals x to the n. If I want the derivative, this is equal to nx to the n minus 1. This is the power rule. N is any real number. Now, I want to give you some examples of this that come up a lot. Suppose y equals the square root of x. But remember that square root of x is equal to x to the 1/2. So y prime is 1/2 x to the negative 1/2 power. Remember that 1/2 minus 1 is negative 1/2. And this is equal to 1 over 2x to the 1/2. But remember that x to the 1/2 is the square root of x. So we can write this as 1 over 2 times the square root of x. And so therefore, y prime is 1 over 2 times the square root of x. Let me give you another example. Suppose y equals 1 over x, but this is equal to x to the negative 1. So y prime is negative 1x to the negative 2, which is equal to negative 1 over x squared. And so therefore, y prime is negative 1 over x squared. Number 2, suppose y equals e to the x. Y prime is e to the x. So not too bad. Number 3, suppose y equals natural log of x, and I want the derivative. Y prime is 1 over x. Okay. Now, let's talk about the chain rule. Now, suppose y is equal to f evaluated at g of x. Remember that f and g are differentiable functions. Okay. Now, I want y prime. I'm going to take the derivative of the outside function, and I'm going to evaluate that at the inside function, which is g of x. I'm going to take that answer, and I'm going to multiply by the derivative of the inside function, g prime of x. Now, let's take a look at an example of that. So, suppose I had the following. Suppose I had we'll call this an example, and we'll call it example 3. Suppose y equals natural log of 1 plus 5x. And I want to find the derivative of that. Okay? So y prime. Now, the derivative of the natural log. So let's remind ourselves. And this is just another way to write it. The derivative of natural log of x with respect to x is 1 over x. So when I look back, I'm going to take 1 over the inside function, which is 1 plus 5x. So I'm going to take 1 over 1 plus 5x, okay? And I'm going to take that quantity and multiply by the derivative of the inside function. And I'm going to write it this way, if you don't mind. So in other words, I'm going to take the derivative of 1 plus 5x with respect to x. It's like I'm peeling an onion, okay? And so, therefore, y prime is equal to 1 over 1 plus 5x times 5, right? Because the derivative of x is 1. And so this is 5 over 1 plus 5x. And that's how you do the chain rule, okay? And this is for rule 4, right? So let's talk about another rule. Now, we're going to circle back slightly here. Suppose y equals a to the x power, okay? Now, let's see if we can reason this a little bit. This is equal to e to the natural log of a to the x. But if I apply the properties of logs, I can write this as e raised to the x times natural log of a. Okay? Now watch what happens here. If I want y prime, now I claim that the inside function is x times the natural log of a. Okay? So I'm going to take e to the x times natural log of a, right? Because remember that the derivative, I can write it over here, the derivative of e to the x with respect to x is e to the x. So I'm taking e to the raised to the inside function, which is x times natural log of a. But remember, I have to take that quantity and multiply by the derivative of x times natural log of a. Now, don't get thrown off by that because natural log of a is just a number. Okay? Excuse me. Now, e to the x times natural log of a is just a to the x. So I'm going to write an a to the x there. And the derivative of x with respect to x is 1. And so I'm left with natural log of a. So y prime is a to the x natural log of a. A is greater than 0. A cannot equal 1. Or this doesn't make sense. Okay? That's how you do problem 5. Let's take a look at an example here. Now, suppose I had y equals 3 to the x. So y prime is 3 to the x times natural log of 3. That's it. Now, by the way, I do want to circle back to this. Here's the thing. If a is 1, right, 1 to any power is 1, and then you end up just taking the derivative of a constant, which ends up being 0 anyway. So we restrict our attention to exponential functions. That's why a is not 1. Okay. Now, on number 6, what if y is equal to log base a of x? Okay. a greater than 0, a does not equal 1. So what do I do with that? Well, let's see if we can reason this out a little bit. So I'm going to write this as an exponential function. So I'm going to take a to the y, and I'm going to set it equal to x, just like this. Now I can take the natural log of both sides. So natural log of a to the y is equal to natural log of x, right? Now I can move the y out in front of the natural log. So y natural log of a equals natural log of x. But if I solve for y, I get natural log of x divided by the natural log of a. That allows me to take y prime. Okay? Now, y prime is 1 over the natural log of a, that's just a number, and I'm going to multiply by the derivative of natural log of x with respect to x. But the derivative of natural log of x with respect to x is 1 over x. So this is 1 over the natural log of a times 1 over x. And so therefore, y prime is 1 over x times the natural log of a. So I relate it back to the natural log. Okay, so notice it's 1 over x times the natural log of that base, right there. For example, suppose y equals log base 5 of x, and I want y prime. So this is 1 over x, and I'm going to multiply by natural log of the base. You're done. So I think that's pretty slick. Okay? And that was Formula 6 or Rule 6. Let's take a look at 7. Now, from here, what I want to do is take a look at the 6 trigonometric functions. Suppose y equals sine of x. Y prime is cosine of x. Number 8. Suppose y equals cosine x. Y prime is negative sine x. Number 9. Suppose y equals tangent x. Y prime is equal to secant squared of x. So these are the derivative of the 6 trigonometric functions. Number 10, suppose y equals cosecant x. Y prime is negative cosecant x times cotangent x. Number 11, suppose y equals secant x. Y prime is secant x tangent x. Okay. And then finally, number 12, if y equals cotangent x, y prime is negative cosecant squared x. All right. Now, I want to do a couple more. All right. Now, what if y equals, we'll call this number 13. Suppose y equals arc sine x. Y prime is 1 over the square root of 1 minus x squared. this comes up a lot, and we have to be familiar with this fundamental derivative. Number 14, suppose y equals inverse cosine x. So notice it begins with a c, right? So y prime is -1 divided by the square root of 1 minus x squared. And then we're going to stop at 15 for the review of these derivatives. So if y equals arctangent x, y prime is 1 over 1 plus x squared. Now, so what I want to do from here is I want to take a few derivatives. So the directions say to calculate y prime. And I want to first start off with this example. Suppose y equals secant of 1 plus x squared. So this is a classic chain rule problem. So if I want y prime, so there's a couple things. Remember that the derivative of secant x with respect to x is secant x times tangent x, right? So the outside function is the secant function. So I'm going to take secant and I'm going to evaluate it at the inside function. Okay. Here, see if I could write a clear E. And then I'm going to multiply by tangent of 1 plus x squared. But remember, I have to take that quantity and I'm going to multiply by the derivative of the inside function. So in other words, I'm going to multiply by the derivative of 1 plus x squared with respect to x. Okay, it's like I'm peeling an onion. And so therefore, y prime, the derivative of x squared with respect to x is 2x. The derivative of 1 with respect to x is 0. And so this is 2x secant of 1 plus x squared tangent of 1 plus x squared. That's how we do the first one. Let's take a look at the second one. Suppose y equals 3 to the x times natural log of x. Now, remember, the derivative of 3 to the x with respect to x is 3 to the x times natural log of 3. So I'm going to take 3 to the x natural log of x, natural log of 3, right? And then I'm going to multiply by the derivative of the inside function with respect to x. And that inside function is x times natural log of x. So in other words, I'm going to take 3 to the x natural log of x times natural log of 3 times the derivative of x natural log of x with respect to x. So this is 3 to the x natural log of 3 times natural log of 3 times x. I'm going to apply the product rule here. So it's x times the derivative of natural log of x, which is 1 over x, plus natural log of x times the derivative of x with respect to x, which is 1. So this is 3 to the x natural log of 3 times natural log of 3 times 1 plus natural log of x. Okay, and this is y prime, by the way. So that's example 2. Example 3. Suppose I had the following. Suppose I had y equals cotangent of 3x squared plus 5. And I want y prime. Well, this is again chain rule. The derivative of the outside function with respect to x is negative cosecant squared. So I'm going to write negative cosecant squared of 3x squared plus 5. And then I'm going to multiply by the derivative of that inside function. Again, think about like peeling an onion, right? And so y prime is negative cosecant squared of 3x squared plus 5 times 6x. And then I can write this as negative 6x cosecant squared of 3x squared plus 5. And again, this is y prime. So I'm going to stick to a chain rule theme mostly. And with that, let's take a look at this one. Suppose y equals natural log of x natural log of x, okay? And I want y prime. So the outside function's the natural log function. So I'm going to take 1 over x times natural log of x. Okay. And I'm going to multiply by the derivative of the inside function with respect to x. So in other words, I'm going to take 1 over x ln x and multiply by the derivative of x ln x with respect to x. But remember, we just did that, right? So y prime is 1 over x natural log of x times 1 plus natural log of x. So remember, we did that by the product rule. And that's how we do example 4. And let's take a look at example 5. Suppose y equals e to the cosine x plus cosine of e to the x. It's very different. And I want to find y prime. Well, this is e to the cosine of x times the derivative of cosine x with respect to x. Remember, this is like peeling an onion. The derivative of cosine x with respect to x is negative sine x. Okay. Now, for the second term, the outside function's the cosine function. The derivative of cosine is minus sine. But remember, I'm taking sine and evaluating at e to the x. That's the inside function. And then I get to multiply that result by the derivative of the inside function, which is just e to the x. So this is minus sine x, e to the cosine x, minus e to the x, sine of e to the x. And again, this is y prime. And that's example 5. Let's take a look at example 6. Suppose y equals natural log of secant of 5x plus tangent of 5x, and I want the derivative. So I'm going to take 1 over the inside function, which is 1 over secant 5x plus tangent 5x. And I'm going to take that and I'm going to multiply by the derivative of the inside function. And the inside function is secant 5x plus tangent of 5x, like so. So y prime is 1 over secant 5x plus tangent 5x. I'm going to take that answer and I'm going to multiply by. Now, let's start with the second term. The derivative of tangent of 5x with respect to x is secant squared of 5x times 5, right? Because that's the derivative of the inside function. And then I'm going to go plus, and then I'm going to get secant of 5x tangent of 5x times 5. Okay. Now, I'm going to factor out a 5 secant 5x. So I get 1 over secant 5x plus tangent of 5x. Now, I'm going to take that. I'm going to factor out a 5 secant of 5x and multiply by secant 5x plus tangent 5x. But look what happened. The secant 5x plus tangent 5x factors cancel. And it's not a coincidence. This says y prime is 5 secant 5x. And that's a really good stopping point for this video. And so this is a video on, I would think of this as a differentiation review. And we went over 15 fundamental derivatives and did 6 examples where we found y prime utilizing primarily the chain rule. Okay, thank you.